I now take up section 9.2, and here we talk about a first derivative test for extreme points. In this case, let's suppose we have f of x, and this is a differentiable function of x, and it is differentiable on the interval I. Suppose this function has just one stationary point, and the stationary point is x is equal to little c. Now if we have f prime x greater than equal to 0 for all x belonging to the interval I, but we keep this in mind that x is less than equal to little c, and if we have f prime x less than equal to 0 for all x belonging to I, such that x is actually greater than equal to c. What I mean from the first expression, from the first statement, we see, so first we have f prime x greater than equal to 0 for all x belonging to the interval I, x less than equal to c. That means to the left of c, f of x is increasing because f prime x is greater than equal to 0. And if we think of the second point, that is f prime x less than equal to 0 for all x belonging to I, such that x is greater than equal to little c. That means if we think of to the right, we think of the points to the right of c, we see that we examine that the function is actually decreasing to the right of c, because x greater than equal to c and I is a big word, because for x greater than equal to c, what we examine here is that f prime x is less than equal to 0 for all x belonging to the interval I. That means f of x is decreasing to the right of c. So this we can write that to the left of c, f of x is increasing, to the right of c, f of x is decreasing. To the left of c it is increasing, to the right of c it is decreasing. What it means is that if we think of to the left of c, that means x less than equal to c, for x less than equal to c, f of x is increasing. That means f of x is less than equal to f of c, because f of x is increasing till the time we reach c. And when I say increasing, we are actually, and if I'm not specifying strictly increasing, that means the function is clearly not decreasing to the right of c. So f of x is less than equal to f of c for all x less than equal to c. And I can see that for all x greater than equal to c, that is to the right of c, f of x is decreasing. Clearly that means it is not increasing, it is decreasing. So that means f of x is greater than equal to f of c. Or I can write f of c is okay, so it's f of x less than equal to f of c, f of x greater than equal to f of c. So I can write in this case, because when we are to the right of c, x greater than equal to c, f of x is decreasing. So for x greater than equal to c, f of x is less than equal to f of c. Or I can write f of c is greater than equal to f of x. Basically, to the left of c, the function is increasing. To the right of c, the function is decreasing. And I think it's intuitively clear that if to the left of c, the function is increasing, to the right of c, the function is decreasing, that means x is equal to c would be the maximum point for f in the interval I. And that just means that x is equal to c is the maximum point for f in the interval I. We can have a look at the diagram, and we see the diagram now, this. And here we see that if you look at figure 9.5, you see that the function is increasing to the left of c and it is decreasing to the right of c. That just means x is equal to c is the maximum point. So f prime x is greater than equal to 0 for x less than equal to c. F prime x less than equal to 0 for x greater than equal to c. That just means that x is equal to c is a maximum point for f. Similarly, if you look at figure 9.6, here we see that the point x is equal to d, it is a minimum point. Why do I say this? Because when x is less than equal to d, f prime x is less than equal to 0. What does that mean? That means the function is decreasing to the left of c, to the left of d. And I see that f prime x is greater than equal to 0 for x greater than equal to d. That means the function is increasing to the right of d. So in this case, in figure 9.6, we see that the function is decreasing to the left of d and it is increasing to the right of d, and that just means that x is equal to d would be the minimum point for f. In other words, I can summarize actually everything by this. So if I want the first derivative test, so this is the first derivative test for maximum or minimum. The first thing to note is if f prime x is greater than equal to 0 for x less than equal to c, and f prime x less than equal to 0 for x greater than equal to c, then x is equal to c is a maximum point for f. What is the reason? Because if f prime x is greater than equal to 0 for x less than c, that means the function is increasing to the left of c and it is decreasing to the right of c. And that just means that x is equal to c would be the maximum point for f. The second point to note here is that if f prime x is less than equal to 0 for x less than equal to little d, and f prime x greater than equal to 0 for x greater than equal to little d, then x is equal to d is a maximum point, not maximum, then x is equal to d is a minimum point for f. Then x is equal to d is the minimum point for f. So what we see here is that f prime x is less than equal to 0 for x less than equal to d. It is greater than equal to 0 for x greater than equal to d. That just means that the function is decreasing to the left of d and it is increasing to the right of d, and that just means that x is equal to d would be the minimum point for f. Now let's take up a question to understand all this. So let us say measured in milligrams per liter, the concentration of a drug in the bloodstream T hours after injection is given by the formula C prime T is equal to T divided by T squared plus 4. So what is this? This is the concentration of drug in the bloodstream T hours after injection. And we have to find the time of maximum concentration of that drug in the bloodstream. We have to find the time of maximum concentration. So the way we proceed here is that first we have C of t upon t squared plus 4. So what we do is we differentiate with respect to t, because we want to find out the time of maximum concentration. That means we are going to so this is the concentration given and we want to basically maximize this. And for that what we do is first we differentiate this with respect to t, and that means I want C prime t. So I use the quotient rule and I get this t squared plus 4 squared in the denominator, and then what I do is I write t squared plus 4 1 minus t 2t. So this gives me t squared plus 4 minus 2t squared divided by t squared plus 4 squared, which is equal to 4 minus t squared by t squared plus 4 squared, and that is 2 minus t 2 plus t divided by t squared plus 4 whole squared. Now in this case we are always concerned about we're concerned about the term t. We want to find out the time of maximum concentration, and time is always positive. So basically here we are going to ignore this. The reason I'm talking about this is that if you think of, let's equate C prime t to 0. If I equate C prime t to 0, obviously in this case I can see that the denominator is always greater than 0, and I can think of, if I want to equate C prime t to 0, I will have this 2 minus t 2 plus t equal to 0, and that means t is equal to minus 2, t is equal to 2. I can't think of t is equal to minus 2, t is time. So we are just concerned about this. And what we see is that if t is less than equal to 2, c prime t is greater than equal to 0. Because I'm only concerned about, as I said, I'm only concerned about this. If t is less than equal to 2, that means 2 minus t. If I think of 2 minus t greater than equal to 0, that just means it is this, or t is less than equal to 2. And when is this the case? C prime t less than equal to 0. That means t is greater than equal to 2. That's when this is the case. So t greater than equal to 2, for t greater than equal to 2, we have c prime t less than equal to 0. For t less than equal to 2, c prime t is greater than equal to 0. What I mean to say is that to the left of t, the function is increasing. To the right of it, the function is decreasing. And that means t is equal to 2 would be the maximum point. And that means t is equal to 2, that maximizes c of t. So what I mean to say here is that if we want to find out the time of maximum concentration, that means we can say the concentration of the drug is highest after 2 hours of injection. So after 2 hours of injection, as in after 2 hours the drug is injected into the bloodstream, the concentration is highest. So that means we can say, if this is the case, that means this maximizes C of t. And this just means that, therefore I can write, therefore the concentration of the drug is highest 2 hours after injection. And if we think of what is C of 2, C of 2 is equal to 2 by 2 squared I know is 4 plus 4. So that is 2 by 8, which is equal to 0.25. And that means the maximum concentration is 0.25 milligrams per liter. Let's take up another question. Suppose we have y of n, and these many bushels of wheat are harvested per acre of land when we use n pounds of fertilizer per acre. So per acre, if we use n pounds of fertilizer, we get y of n bushels of wheat. So it's all per acre of land. So the point to note is, this is these many bushels of wheat per acre of land are harvested when n pounds of fertilizer per acre of land are used. So this is what we have with us. And let's say P is the price per bushel of wheat. That means each bushel of wheat, the price of each bushel of wheat is P. So P is the dollar price. So let's say P is the dollar price per bushel of wheat. And let's say Q is the price per pound of fertilizer. So each pound of fertilizer, its price is Q. So let's say Q is the dollar price per pound of fertilizer. Then if we are concerned about the profits per acre, and profits are all obviously here in dollars, profits per acre of land, what would that be? So that would be, in fact, so per acre of land we get these many bushels of wheat, and the dollar price per bushel of wheat is P. That means I have P multiplied by Y of N, and this is the output, this is the value of the output. But what is the value of the input that goes in? We are using N pounds of fertilizer per acre of land, and each pound, the price of each pound is Q dollars. So that means I should go for minus QN, and this is my profit, which is a function of N I see here. And what is N? N is, as I said, N is the pounds of fertilizer per acre of land. So N pounds of fertilizer per acre of land are used. So on each acre of land we are using N pounds of fertilizer. So N is either greater than or equal to 0. Now let us say we've still not formulated the question. Let us say here we have some N star, and for this N star, and if we think of pi prime N, it is greater than equal to 0 for N less than equal to N star, and pi prime N is less than equal to 0 for N greater than equal to N star. That means the profit function is increasing to the left of N star and it is decreasing to the right of N star. What that means is that this N star is actually maximizing our profit. And in that sense, N star would be maximizing our profit, and we will then see that pi prime N star would be equal to 0, because the point is that from this we see that pi prime n is greater than equal to 0 for n less than equal to N star. It is less than equal to 0 for n greater than equal to N star. Then that means obviously pi prime N star will be equal to 0. So, and also we see that this N star is actually maximizing our profit, because the profit function is increasing to the left of N star and it is decreasing to the right of N star. So that means I can write that N star maximizes for some n star. We have not yet established what this n star is. So then I can say that n star maximizes profit and pi prime n star is in fact equal to 0. So now I know what pi of n is. I now actually calculate pi prime n star. So I write again pi of n, which is equal to p y of n minus qn. Now in this case, pi prime n is equal to p y prime n minus q. This should be made equal to 0, and if that is the case, we see that p y prime n star is equal to q. Now let's try to in fact give an economic interpretation to this condition. This has to be satisfied if n star maximizes profit, because if n star maximizes profit, I know that pi prime n star is equal to 0. I also know that to the left of n star the profit function is going to be increasing. To the right of n star the profit function is going to be decreasing. So let's try to give an economic interpretation to this particular condition. And here let's suppose that we are using n star units of fertilizer. We are using n star units of fertilizer. What we have now proposed till now is that n star maximizes profit. Let's try to understand how that is the case. So let us say we are using n star units of fertilizer, and think of the fact that we are trying to increase this n star by 1 unit. We think of increasing n star by 1 unit. Now what is it that I gain when I increase n star by 1 unit? N star is the number of pounds of fertilizer per acre of land that I'm going to use. So if I'm using n star units of fertilizer, or in other words n star pounds of fertilizer, it's one and the same thing, and I want to increase n star by 1 unit, or in other words I want to increase n star by 1 pound, what is it that I gain? If let's say, let's not get into pounds, let's just think of that unit case. So if I increase n star by 1 unit, then what is the gain? For that we have to obviously think of the fact that if I put in more fertilizers, I will get more bushels of wheat. So that means if I increase n star by 1 unit, so I will get, so in this case I was getting these many bushels of wheat, but if I increase n star by 1 unit, I will get n star plus 1. This is what this is the number of units of fertilizer that I now put in, and what is the outcome that I get? Y n star plus 1. So if n star increases by 1 unit, then if I'm asked how many more bushels of wheat are produced, so if n star is increased by 1 unit, these many bushels of wheat are produced. These many more bushels of wheat are produced, and we are going to say that this is approximately equal to this y n star plus 1 minus y n star this is approximately equal to y prime n star. So when I talk about y prime n star, what does it signify? As n star increases by a really small amount, what is the change in y? In fact, that change in n star, that small increase in n star, or that small change in n star I'm concerned about, that change itself tends to 0. So for an infinitesimal change in n star, what is the increase, or what is the change? In fact, I should say, what is the change in y? But if I'm concerned about that infinitesimal increase in n star, or infinitesimal change in n star, and here I talked about increasing n star by 1 unit, so we are more or less thinking that if you have so many pounds of fertilizer being used on 1 acre of land, if you just think of increasing that fertilizer units, increasing the number of units of that fertilizer by just 1, that's almost equivalent to, or that's approximately equivalent to increasing n star by a really small amount. So in that sense, we are saying that y of n star plus 1 minus y of n star is approximately equal to y prime n star. And the point to note is that these many extra bushels of wheat will be produced when we increase n star by 1 unit. Now for each of the bushels of wheat that are harvested, for the price of each bushel of wheat is p dollars. For each of these bushels, for each of these extra bushels of wheat, we get p dollars. What does that mean? That means I can say that by increasing n star by 1 unit, we gain approximately this much, p multiplied by y prime n star. These many dollars we gain. Also, I know that if I increase n star by 1 unit, obviously if I'm putting 1 extra unit of fertilizer, I'm actually incurring the cost of that fertilizer. And we know that 1 unit of fertilizer, or 1 pound of fertilizer, the price of 1 pound of fertilizer is q dollars. So that means I can now write that by increasing n star by 1 unit, we lose q dollars. When I say unit, I mean pound, because q is the cost of 1 unit of, q dollars is the cost of 1 unit of fertilizer. So now we can interpret our condition. The condition was p y prime n star equal to q. And here we see these two cases, this and this. So the point to note is that if I want to maximize my profit, I have to increase the amount of fertilizer to the level n star, and at n star, an additional pound of fertilizer equates my gains and losses, because now once I have reached n star, and now if I increase n star by 1 unit, what we gain is exactly what we lose. This is what is given by this condition. So that means, again, if I want to maximize my profit, I have to increase the amount of fertilizer to the level n star. And once we reach n star, at that level, if there is an additional pound of fertilizer that we use, that leads to equal extra gains and losses. That equates our gains and losses. So that means I can say here that in order to maximize profit, we should increase the amount of fertilizer to the level N star. At N star, an additional unit of fertilizer here we see that the gain is this, the loss is this, and at N star, if this is the case, that means at N star an additional unit of fertilizer equates gains and losses. Given all this, let's take up this question. In a certain study, from Iowa in 1952, the yield function, which is y of n, the yield function was estimated as this. Y of n equal to minus 13.62 plus 0.984 n minus 0.05 n raised to the power 3 by 2. Now let's say price of wheat, which is P, it is $1.40 per bushel, and price of fertilizer is $0.18 per pound. We have to find the amount of fertilizer that maximizes profits. For that, what we have to do is we have to understand what pi of n is. What is the profit? Pi of n is, I know it's Py of n minus Qn. So I can now write pi of n is equal to, it is 1.4, and now I write that function, the yield function, which I know is minus 13.62 plus 0.984 n minus 0.05 n raised to the power 3 by 2 minus Qn. Now Q is 0.18, so I'll just write minus 0.18 n. And here what I do is I will actually equate pi prime n, I will calculate pi prime n, and I will equate it to 0. If I calculate pi prime n, it will turn out to be 1.4. I don't take into account this minus 13.62. I then write 0.984 minus, it should be 3 by 2, 0.05 n, 3 by 2 minus 1, so it will be 1 by 2. This minus 0.18. This should be equated to 0. And when this is equated to 0, what do I have? That means I have 1.4 multiplied by 3 by 2 multiplied by 0.05. Then it is n raised to the power half. So it's actually this. And this should be equal to 1.4 0.984 minus 0.18. And now I can calculate n star from here. In fact, n star raised to the power half is equal to 1.4 0.984 minus 0.18 divided by 1.4 3 by 2 0.05, and this is in fact equal to 1.1976 by 0.105, which is approximately equal to 11.406. That means I can now take up what n star is. N star will be, in fact I should again write approximately equal to 11.406 raised to the power 2, which is approximately equal to 130. That means approximately 130 pounds of, and in fact I can't say that right now, so we have to actually see that if we see pi prime n, let's take a look at this expression. This is pi prime n. What we see here is that this expression is in fact greater than equal to 0 for n less than equal to n star, which is around 130, and also we see that pi prime n is less than equal to 0 for n greater than equal to n star. So what we see here is that our profit function is increasing to the left of n star and it is decreasing to the right of n star, and that means when I talk about n star, and we know that n star is what corresponds to the first derivative of the profit function being set to 0. So then we see that this n star, which is approximately equal to 130, this maximizes profit, and hence I can write n star, which is approximately equal to 130, this maximizes profit. Let's take up another question. And here we take the case of a student, and the student has current income y1 and she expects future income y2. So this is the current income, and let's say this is the future income. Future expected income or expected future income. Now she is going to plan current consumption and she's going to plan future consumption. So current consumption is this and future consumption is this, and her motive is to maximize the utility function. Her utility function is this. Utility function which is to be maximized is this. utility function is ln c1 plus 1 upon 1 plus del ln c2. This is the utility function. Now what is this delta or this del? This is her discount rate. And let's say, so the point to note here is, till now what we have understood is that there is a student whose current income is y1 and she expects future income y2. She is going to plan her current consumption and her future consumption, C1 and C2 respectively, and her motive is to maximize the utility function. And what is her utility function? It is ln C1 plus 1 by 1 plus del ln C2, and here this delta is her discount rate. Let's say in the current period she borrows, and if she borrows, that just means that her income is not able to meet her consumption, in the sense that C1 is actually greater than Y1 if she borrows. And if she borrows right now, what does that mean? That means if she borrows now, she will have to repay the loan amount along with interest in the future. So as far as her future consumption is concerned, her future consumption would be only after she has repaid the loan amount. So if this is the case, if her current consumption is more than her current income, that means she is going to borrow. And what is it that she's going to borrow? She's going to borrow this much. And once she has repaid this amount, this loan amount, with interest charged at rate, let's say R, so that means, okay, so if this is what she has borrowed and she is going to pay the interest the interest is charged at rate R. So what is it that she has to repay in the future? She has to repay this much. This is what she has to repay. And her future income, and as far as this is concerned, this is what she has to repay, and this is what she repays out of her future income, and whatever is left is going to be her future consumption. So her future consumption in that sense would be C2, which is equal to Y2 minus this. So this is what she has to repay, and whatever is left, that is going to be consumed by that student in the future period. There are only 2 periods. So this is going to be her future consumption in this case. This is when she borrows in the first period. Now let's say she does not borrow in the first period, she is going to save in the first period. If she saves in the first period, that just means that her consumption is in fact less than her income. So the remaining amount, or the difference, is what she is going to save. So if she is going to save, that just means C1 is less than Y1. And what is it that she is going to save then? Y1 minus C1. As far as her future consumption is concerned, in future her income will actually be increased, because if this is what she saves, that means this is how much she lends, and if she saves this much, she is going to get some interest back. She is going to receive interest at some rate on her savings. So let us say the interest remains the same. It is interest is charged at rate little r. So what is it that she is going to receive in the future if she saves Y1 minus C1 in the present? She is going to receive this. And in the future, as I said, there are only 2 periods. So in the future, what is it that she has with her? She has her future income and this. So she has all of this to consume in the future. So C2 would be equal to Y2 plus this. So this is what C2 is if she is a saver. This is what C2 is if she is a borrower. Now the question is, find the optimal borrowing or saving plan. Find the optimal borrowing or saving plan. Now, in both cases, we see that if the student, okay, let's try to solve this now. Whether the student borrows or whether the student saves, if you just try to solve these two, okay, so this is y2 plus this, and this can also be written as y2 minus c1 minus y1 1 plus r, and this is exactly equal to this. So the point to note here is that whether the student borrows or saves, second period consumption is this C2, which is equal to y2 minus 1 plus r c1 minus y1. Either way, it's going to be this much. And we know that the motive of the student, the goal of the student is to maximize her utility function. Utility function I know is this, let's say it's u, which is equal to ln c1 plus 1 upon 1 plus delta ln c2. Now what we do is, instead of c2, we write this expression. So I can now write u is equal to ln c1 plus 1 upon 1 plus delta ln. Now I can write what c2 is. So it is y2 minus 1 plus r y c1 minus y1. Now what we do is, we are going to differentiate this function with respect to c1. And when we do that, we get this du by dc1 is equal to 1 by c1. Now I should go for, I should actually go for this. We have to differentiate this with respect to c1, so I should go for minus 1 plus r, and then I should go for 1 plus delta, and then it is y2 minus 1 plus r c1 minus y1. In fact, I could have written it this way. That would have been better to understand. I can use the chain rule. I have to differentiate this with respect to c1. So I should go for 1 upon 1 plus delta. Then it is 1 upon y2 minus 1 plus r c1 minus y1. And then I should go for, it should be minus 1 plus r. And now this can be written as 1 upon c1 minus 1 plus r by 1 plus delta 1 upon y2 minus 1 plus r c1 minus y1. And this can then be written as, let's just try to have a common denominator. So that common denominator can be this much. It will be c1 1 plus delta y2 minus 1 plus r c1 minus y1, all of that. So I just write c1 1 plus delta, and then it should be y2 minus 1 plus r c1 minus y1, this, all of this. And then I can write here I should write 1 plus delta y2 minus 1 plus r c1 minus y1, and it is then minus 1 plus r c1. So first we just think of this, and then we have all of this. So it's first 1 plus delta, then this expression, and then minus 1 plus r multiplied by c1. So it's this. Now what we do is that we are going to equate the derivative to 0, but before that we would like to take up the numerator separately and kind of rearrange it. So I know that I'm going to set this derivative du by dc1 to 0 precisely because I want to know, if you can recall, the question was that we have to find the optimal borrowing or saving plan. So that means we have to think of what is C1, and once we get C1, we will examine what is the optimal borrowing or lending plan. And when I say optimal, that means the one that maximizes the utility function. So what I now do is I take up the numerator separately, and I would like to rearrange the numerator. So this I can do here. So this can then be written as, in that, I mean, the point that I'm trying to make is that I want to rearrange the numerator. For that, it will take a little time, but it will give us 1 plus delta y2 minus, so we open up this, y2 minus c1 minus y1 plus rc1 minus ry1, and then it is minus 1 plus r c1. This can then be written as 1 plus delta y2 minus c1 plus y1 minus rc1 plus ry1 minus 1 plus r c1. This can then be written as 1 plus delta. Then we have, if we take up y1, there is y1 plus ry1 here. So we take up 1 plus ry1, and if you take up C1, you have C minus here, minus 1, and you have minus r here. So I can then write 1 plus r y1 minus 1 plus r c1, and then I can just write plus y2 minus 1 plus r c2, 1 plus r c1. Now I can write 1 plus delta 1 plus r y1 minus 1 plus delta 1 plus r c1 plus 1 plus delta y2 minus 1 plus r c1. I can write this now. And now what I can do is I can take up these and this, and when we do that I get 1 plus delta is out, it's common, and then I have 1 plus r y1 plus y2. Also I have this and I have this. You can see something common here, and that is minus 1 plus r c1. So that is what I get, and then I write 1 plus delta plus 1, and this gives us 2 plus delta. So instead of this now I can write 2 plus delta, and that means my numerator becomes 1 plus delta 1 plus r y1 plus y2 minus 2 plus delta 1 plus r c1. And now I can write this in my numerator. So now I can write du by dc1 is equal to 1 plus delta 1 plus r y1 plus y2 minus 2 plus delta 1 plus r c1, and this divided by that same denominator, which is c1 1 plus delta y2 minus 1 plus r c1 minus y1, and this has to be set equal to 0. Now if you want the solution to this, obviously we have to think of, so now c1 star will be equal to 1 plus delta 1 plus r y1 plus y2 divided by 2 plus delta 1 plus r. This is my c1 star. And in fact, if we look into this carefully, we will have this. This can then be written as so let's take up this expression separately. It is 1 plus delta (1 plus r y1 plus y2) divided by 2 plus delta 1 plus r. Now this can then be written as 1 plus delta 1 plus r y1 by 2 plus delta 1 plus r plus 1 plus delta y2 by 2 plus delta 1 plus r. You can see here that here you can okay, I think we can proceed this way. In this case, instead of what is written here, when it is written y1, where it is written y1, so instead of 1 plus delta, I can actually write 2 plus delta minus 1. I can write this 2 plus delta minus 1. I can write it this way. This 1 plus r y1. And this divided by 2 plus delta 1 plus r plus 1 plus delta y2 by 2 plus delta 1 plus r. Now this can then be written as 2 plus delta 1 plus r y1 minus 1 plus r y1 divided by 2 plus delta 1 plus r, and then plus this expression 1 plus delta y2 by 2 plus delta 1 plus r. And now this can be written as y1 plus 1 plus delta y2 minus 1 plus r y1 divided by 2 plus delta 1 plus r. So this is also my C1 star. So I can say that C1 star is equal to this also. Now, if I see that if C1 is greater than C1 star, and if you now look at what is your du by dc1, du by dc1 is this. Okay, I think I can think of du by dc1 here this way. In this manner, I think we can write. This is our du by dc1. C1 star is this. You see here that if your C1 is greater than the C1 star, du by dc1 will be less than 0. And it's very clear from these two expressions. If C1 is greater than C1 star, then du by dc1 is is less than 0. Here we can see this. If C1 is greater than this expression, then clearly du by dc1 is going to be less than 0. And also if C1 is less than this expression, C1 star, then du by dc1 is greater than 0. So what we see is that if we are to the left of C1 star, the function is strictly increasing. If we are to the right of C1 star, the function is strictly decreasing. And that just means that the C1 star clearly maximizes the utility function. And this just means that C1 star indeed maximizes U. Alright, so we get that optimal C1 star. From this optimal C1 star, we can easily get to we can easily get to the optimal C2 star. But the point is, we wanted to know the optimal. The question was that we wanted to find out the optimal borrowing or saving plan. That was our question in the first place. So we have still not got there. We still don't know about the optimal borrowing or saving plan. For that, we have to take help from this expression. And when we take help from this expression, you see that C1 star is equal to this, y1 plus whatever is given here. If the student lends, that just means my C1 is greater than y1, and that means this expression is positive. I think I've made a mistake here. That's not the case. When I say that C1 is greater than when the student is lending, if the student is lending, that just means C1 is less than Y1, not C1 is more than Y1. If the student is lending, that means her current consumption is less than her current income, and only then she is able to save or she will be able to lend. So if the student lends, so in the optimal scenario, if the student lends, or I can write it this way. Before writing, let's try to understand this, that the student lends. If the student lends, that means C1 star is in fact less than Y1. And if it is less than Y1, that means this expression is negative. And if this expression is negative, that means 1 plus delta y2 is less than 1 plus r y1. So if this is the case, then the student is going to lend. Or if the student lends, then this is the case. So I can then write the student lends if and only if 1 plus delta y2 is less than 1 plus r y1. And in the other case, the student borrows. So the student borrows if and only if 1 plus delta y2 is greater than 1 plus r y1. Why do I say this? Because if the student is borrowing, that just means her current consumption is less than her current consumption is more than her current income. And if it is more than that, that means this expression is positive. And if it is positive, that just means 1 plus delta multiplied by y2 is greater than, it is greater than 1 plus r multiplied by y1. And now clearly this is the more likely case, because here you are actually comparing this 1 plus delta multiplied by y2 with 1 plus r multiplied by y1. Now more often than not, in a student scenario, the future expected income or the expected future income is considerably higher than the present income. So y2 is really much higher than y1. So even if 1 plus delta and 1 plus r, they are, as in, even if delta is less than r, but y2 will be considerably higher than y1, and that just means that this is the more likely scenario wherein 1 plus delta multiplied by y2 will be much more than 1 plus r multiplied by y1, and in this case the student is going to borrow. By chance, if 1 plus delta y2 is exactly equal to 1 plus r multiplied by y1, in that case the student will neither be a borrower nor will she be a lender. So this is the optimal borrowing or lending plan that we have to understand. The student lends if and only if this is the case. The student borrows if and only if this is the case. Here you can say that this is more likely because y2 is considerably higher than y1 in the student's case. Also, I can then write, by chance, if 1 plus delta y2 is equal to 1 plus r y1, then the student will neither be a borrower nor a lender. So what we have studied in this section is that when we talk about the first derivative test, that's the section 9.2. When we talk about the first derivative test for extreme points, so what we do is we first calculate the first derivative, set it equal to 0, but that's not sufficient for us to conclude that what we have got is a stationary point. We don't yet know if it is a maximum point or a minimum point. For that we have to take the first derivative test, and if we take the first derivative test, what we see is that if the function is increasing to the left of that point and decreasing to the right of that point, in that case the point is maximum. In that case we have the maximum point with us. If the function is decreasing to the left of that point and increasing to the right of that point, in that case we have a minimum with us. So the first derivative test for extreme points is, number 1, we are going to calculate f prime x and set it equal to 0, and number 2, we have to see the sign of the first derivative. We have to see the sign of first derivative to the left and the right of that x is equal to c or that x is equal to d, depending on, and then we can see whether we have a maximum point or we have a minimum point.